Good morning. So my name is Jaap from the Beek, and I will talk about wireless access in rural regions. Yeah, you can probably tell from my name that I'm originally from the Netherlands, and that being one of the most populated parts of Europe doesn't give me necessarily the authority to talk about rural regions, but I'm with Luleå University of Technology, which is in the far north part of Sweden, and that is one of the most remote and large areas remaining in Europe today. So we have a perspective in this talk from exactly northern Sweden. So we have scenarios in mind, like you see here, scenarios where there's few people per area, very sparsely populated regions, large areas, pretty limited access to fiber networks, or at least long distances to the nearest fiber networks at places. Same for electricity networks. Roads infrastructures are very sparse. On the other hand, there is an abundance of radio spectrum. So much of the spectrum is not used today, or even though it is licensed by national operators or others. So typically in these regions, the spectrum issue is not immediately a problem for access. And so I used to start my presentations with showing this phone, which most of you will remember as one of the first generation analog cellular phones. This is one phone from the 80s, I guess, by Ericsson. And for many of us, we will look at this as a reminder how fast developments have gone, and how much technology has been evolved during the last four decades. But for people in the north of Sweden, many of them look at these instead with some kind of nostalgia, because in one way this phone performs better than today's 4G or 5G phones. It had much better coverage. People think or remember this phone as a very reliable tool wherever you were in the forest or away from home. This phone could call home. So in one way, this phone is worse, and the question is, of course, why have new generations of cellular telephony not improved in that sense, while they have so much in other senses? So internet everywhere, that is what geographically everywhere. That seems to be a very difficult challenge for the community to solve. And there is large values, at stake for that, and they are being more prominent, for every day, visible. In the end, this divide between the urban and the rural is about democracy and the hope for a better future for many people, and the cellular coverage is instrumental for that. For this feeling or sense of inclusion. But also there's large values at stake, economic values, public safety also, not the least. The societal values, for instance. We have public services that needs to reach all the citizens everywhere. We want rural regions, often to be attractive. We want people to stay there, people who live there. We want people who are not living there to move there. We want tourists to get there. So there is migration and urbanization issues at stake. And like I said, there is safety and security. There's more and more, let's say, demand for connectivity from a point of view of security. Blue light services, you want to call 911 everywhere where you are, etc., etc. So there are forces from the societal point of view that are working for these kind of connectivity in these rural regions. But there's also many economic values. These are just to name a few. There's in the north of Sweden, we have forestry, we have of course agricultural values, mining, we have power industry, we have tourism. Also the transport, the transport and the logistics, they are facing a huge structural change in the coming decade, going going towards electrical vehicles and autonomous transports, etc. And rural regions are probably the first to really get the fruits of these developments in transports. This is where the economical values of autonomous transports will pay off first, because distances are so large. But to have good transport and logistics sector, we will need connectivity. Whenever these electrical or these autonomous transports vehicles will get outside the coverage area of the internet, they will basically park themselves, even though they could go on and drive autonomously. For legal and safety reasons, they will probably, and logistical regions, they will just park themselves, and you will go and have to get them. So internet and an aerial coverage of internet, it will also be very important for future transport, what is it, transport on land, like we see here in the picture, but also the drones, the airborne autonomous vehicles. So in Sweden, the connectivity targets, they are set politically. So for instance, this is how the European Union and the Swedish government want the Swedes to be connected. So the European says that by 2020, we have a few months left only, all people in the EU shall have access to 30 megabits per second. And it has already been acknowledged by the politicians in Sweden that we will not be able to satisfy that criteria in Sweden. 3% of the Swedish citizens will not have this access. They don't have access today, and we can guess where those 3% of the people actually live. Obviously, that's the rural regions where we just mentioned. The government itself, the Swedish government itself, also has in late 2016, they have announced some strategies, and the horizon for that is 2025. And again, there a large percentage of the people will have very high data rates, but this is in their homes. This is where they live and where they work. But there is another, for the first time in December 2016, the government also added a mobile coverage, a cellular coverage, saying that there should be coverage everywhere where people reside and move typically. Now that's still a very vague goal, and there are forces now that are pushing for a more concrete target for when we're going to update these strategies. But it's a good sign that there is some kind of notion of the importance of cellular coverage and some kind of an aerial coverage coming into these goals. So the question is, going back to this first generation phone, why does cellular networks and standards, why don't they improve the coverage? It appears in every drafting of a new standard, 4G, 5G, it appears as a target in the early days. This was back in 2015 when 5G was being sketched, and there was a clear goal in the original draft about aerial coverage. This time, 5G is being rolled out now, and can we deliver 50 megabits per second everywhere, or will it? And the answer is typically there's no signs that it will. We are still doing business as usual, so networks are being rolled out in the cities first, and then hopefully later on to the rural regions. And the question, so it's again, 5G will be an urban standard. It will be about densification of the networks. It will be about higher data rates, lower latencies, but not necessarily about true aerial coverage. And well, the reason for that is rather simple. There's no, it's not a technical problem. It's not a problem with the standard. It's an economical problem. The rural revenue, potential revenue per square mile per year is simply orders of magnitude lower in the rural regions than they are in the urban regions. So effectively, what we get is a line somewhere in the forest, and it has been there for decades now. A line, if you're living or residing beyond that line, you won't benefit from the advantages of internet. You won't have coverage, and if you were living on the proper side of this line, closer to the urban regions, the market forces will help you to get this internet access. And this line, it depends on the economical business models, the business models of the operator, and the choice, if you want, the choice by the operators whether to deploy the network or not. And there's very little technological dimensions in these choices. It's purely about the competitive markets that reign and govern these decisions. So it's about the cost of the infrastructure, the operational expenditures, and the investments, capital investments, and what we can get back. And this, in most of the networks globally, this has been chosen to be done by market forces, and that has worked very nice in the urban regions. But this line in the forests hasn't been moved, and quite the opposite. It may actually have been moving towards the rural regions, and the situation haven't typically been improved. So how do we assess then this if it's not technical, or if technological innovations have not helped us for the first 30-40 years? How do we approach this? Well, the first thing is to quantify this. It's difficult to visualize and to illustrate how this divide actually how it appears. So we have had a couple of projects in northern Sweden where we try to measure the cellular coverage. The operators, they have their own maps, but we have had we're basically verifying these maps, and we have these kind of backpacks with a large stack of mobile phones, and we have loaded them onto buses, garbage trucks, ambulances. In short, they have been for a year or over a year. A number of these backpacks have been moving around the whole northern region, thousands of square kilometers, and obviously mostly over the roads, and measuring cellular performance or cellular coverage. So this is what the indication of these measurements. They have continuously been measured for a year, and on the top left of this figure you see the coverage maps typically provided by the Swedish regulator. The left figure, the yellow part in the top left figure, is the 10 megabits per second coverage, and the figure next to it is the regions where we have 30 megabits per second of decent quality from a cellular coverage. And the project we're doing now is comparing actually and verifying with these measurements whether these operator provided measures make sense, and because on a more detailed level verify these maps rather than on these national maps. so this is an example from a 350-kilometer trip. All these figures, they show this along the trip from 0 kilometers, the start, to the end of the trip. Basically the measured power, received power of these of the different cellular. This is one cellular network as an example, and it is also the phones are also tracing on the second figure in the middle, how the handover between networks is done. So in the best case, you're connected to the LTE network with a high data rate. But we see that along this road, which is a main road between two cities in this rural region, we have very often we are forced to use the GSM network, and there's even for many kilometers we are outside coverage at all. The signal strength is simply absent. We're in white spaces. So that is one aspect we can do. The second aspect what we have been working on to measuring is, can we actually measure the digital divide? Here's the same figures again, the 10 megabits per second coverage maps to the left, and the 30 megabits per second coverage to the right. So we've been developing an index that actually correlates these coverage maps to the population density in places. So we've questioned how is the question we've asked ourselves is, how is this coverage related and distributed among urban and rural regions of Sweden? Is it more, and obviously it is more tended to the urban regions, and this index, it's very similar to the economical index of the Gini index that economics use to measure inequalities of the distribution of capital or income. So this CCI index, this cellular coverage inequality index, it is a number between 0 and 1, and a low number indicates a small digital divide. A number close to 1 means that it's completely unequal. All the cellular coverage that is actually provided is appearing in the urban regions. So desirable here is a low CCI index. That means that the cellular coverage is completely uniformly distributed across rural and urban regions. But that's not how it's in reality. We see that the CCI index here is in the order of 0.5, 0.6. And that tends to, that this coverage is skewed towards the urban. So this is a powerful measure to use for evaluation of this, of the divide by itself. The coverage itself is also measured here. It's 82% of the country in the left, and only 16% of the aerial, the surface of the country for the 13 megabits per second. So we have, this gives us two measures. Here we have plot them both. On the horizontal x-axis we have the coverage in percent, and obviously we want to move to the right in this figure. 100% coverage is somehow the full coverage is the desired scenario. But we have also on the y-axis now we have this index. So how is it distributed? Where is the cellular coverage provided, in the urban or in the rural? And so overall, the desired direction here is to move to the lower right-hand corner. That is why we have full coverage, and and we want to get lower in this graph with a small CCI index. And we see that the networks are actually doing that. Although the 10 megabits per second, it's actually for the last 2 years, it has been moving up again. So that indicates that the operators are simply filling out now the remaining coverage holes where people actually live, the most urban parts of the country that are still left without coverage. And it is likely that this will never, the current forces will never force this CCI index to 0. So this is a tool that on one way it can be used for evaluation, and on the other hand it could be used for regulatory actions, right? The regulators could force operators to roll out networks with a certain small CCI index, a target index. So solution direction. So what we really want to do here is the engineering challenge is actually to come up with new solutions, to come up with new technologies, if you want, that force this CCI index to a smaller number, so that the rural will get the advantages equally soon, or even and equal to the same extent as the urban does. And that is a difficult thing, because typically as an engineer, if you come up with new solutions, if you do this with the full purpose and the full let's say devotion to have those solutions work in the rural, whenever those solutions become available, it turns out that many of those solutions will work even better in urban scenarios and urban regimes, which means that the solutions, even though they were developed for the purpose of the rural, that they actually increase the CCI index, they increase the divide between the urban and the rural, and they are counterproductive, despite the good intentions. So what we need is technology that exclusively serves the rural more than it does the urban, and that comes to its full effect earlier in the rural than it will in the urban, despite the market forces, despite the economical forces that are obviously in force. So solution directions here. Well, we have to, as a first step, we have to acknowledge that there are these two distinct regimes. To the left, we have the urban regime, and this is that has been working for decades. There are competitive markets. We can have 3 or more networks that are fully competitive, and there is no need. And you have, as a consumer, you choose your description. On the other hand, we have this rural regime where there will never be competition in the same sense. We have to acknowledge and to accept that there will be regions where we have local monopolies, where operators will simply work alone without competition. And in those, we have to somehow accept that we have to design technology and new models and new approaches to have these networks rolled out too, because right now the approach, the urban approach, is not applicable to the rural regimes. So what we need is these local initiatives. We need local networks. We need roaming. We need national roaming in this scenario. Obviously, these phones, they need to be able to roam between these these networks here. We need flexible spectrum licensing regimes. We probably need also some kind of network sharing or infrastructure sharing. This relates also to the issue of roaming. So the architectural, we have in mind, these local rural hotspots here depicted on the lower right-hand side. Small cells, local initiatives with local operators. On top of that, there may be a new national network with ultra large cells, basically wirelessly backhauling or connecting and providing coverage over huge areas. And technology for this has already been available since for 20 years, but there hasn't been any push for these technologies. The key aspect here is that we have to put the base station antennas on a high altitude, and we have an excellent TV tower infrastructure in many countries that is particularly designed to provide these huge coverage footprints from a single tower. So there is a future for these TV towers for broadband connectivity. So basically, conceptually, in the 80s, we had these first generation networks, and it provided pretty large coverage, and even though data rates were small. And then after that, in the 90s, cell sizes shrinked. The density of the networks became higher, but only in the rural regions. Only in the urban regions. The rural regions, the coverage there became worse, and has been so for the second, third, and fourth generation. National operators were focusing more and more on the urban the urban areas. So a future scenario might be that we have this national operator still, the yellow network here, but complemented on one hand by these blue rural and also urban hotspots, locally operated with micro operators, etc. But also complemented with the green network, like an umbrella network based on these high altitude base stations that cover large areas and provide the backhauling for all these small hotspots. So this is an architecture that may hold some potential to break this deadlock that has been and has existed for a long time now. Okay, so the hotspot, the local hotspot, it's remote. You have locally a very high quality network, a very high quality infrastructure, and it becomes like an oasis, a digital oasis, if you want, where the backhauling and the connection to the outside world is the main challenge. We've been piloting this in a number of locations in northern Sweden. We have this. We have installed local hotspots in farms, in forestry locations, in tourist venues, and we have been collaborating with local spectrum licenses, local operated networks, and also with off-grid technology, as I will show in a minute. One notable hotspot that we have installed, it's the top one here on this slide in the mountains here. This is a region where there is it's a very touristic region in the summer and also in the winter. One of the main hiking tracks passes here, so a lot of people, tourists, come in this place. And here we have been we are currently installing an off-grid base station, which is solar powered and provides coverage along the trail, the hiking trail. And this is the view from this place. There is actually, it's not only a tourist spot. There is also a seasonal settlement of the Sami people who live there during parts of the year, and they are also provided with cellular coverage now from this base station. And we're currently exploring now to what extent this battery powered and solar powered base station can provide coverage here. So this is the view in the summer, and this has to be designed very particularly for the weather and the climate conditions here too, also in the winter. Okay, the second part is, as I mentioned, it's the top-down approach. It's a new ways to use the TV infrastructure, and also here we have been we're piloting these. We have been using and mounting large antennas that provide with large number of sectors that provide coverage from a high altitude over cell sizes of tens of kilometers. This is also in a rural place more south in Sweden. So the key characteristics of these towers are really the high altitude of the antenna. The antennas are large, they're modular, they can be up to 20 meters high, which is pretty prohibitive if you mount them on smaller towers. But on these large TV towers, this is fully feasible. Obviously, we need a good uplink, so there need to be some improvements on the UE side as well. So what we've been doing is, first off, we have done a lot of system simulations on this recently, and there's no indication that we cannot reach radii up to 70, 80 kilometers from these towers. So these umbrella networks appear to be fully feasible. And typically it's you would argue, probably what first comes to mind is to use the lower 700 megahertz bands for these networks. And that's where propagation conditions are really favorable. But the problem there is that we have pretty low bandwidth. So if we also want to have a trade-off between capacity and coverage, we would like to use higher frequency bands as well. And it turns out that even the 3.5 gigahertz band, like the medium range bands, when they are properly combined with the 700 megahertz band, it gives a good trade-off for coverage and capacity too. So the most interesting deployment of this technology would be in a combination of these bands. Now I want to finish with a late result or a late development in the regulation of this. So for the 5G, in many countries, in some countries, there have already been an auction for the 3.5 gigahertz band. In Sweden, it's ongoing as we speak. And the thing is that while 5G has a number of various modes and it's an extremely flexible and a standard, there has been these discussions about harmonizing and synchronizing the various deployments and the choices of the deployment modes across countries in Europe to avoid interferences in this TDD deployment across the borders. So this is a document in April 2020 from the GSMA, and basically there's a number of recommendations for how to synchronize and harmonize this coexistence of TDD networks in the 3.5 gigahertz bandwidth, the band. And there has been a discussion, as you see here, and I marked it with red on the top right. There's a number of choices of which kind of TDD configurations we could choose. And apparently the recommendation in April has been to use this configuration that does not allow for longer ranges than 10.7 kilometers by standard, even though by regulation, even though the 5G standard would allow for longer cell sizes, this possibility has now been closed. The door has been closed for this frequency band, simply because this regulation or this recommendation is now being taken over by many countries, and this will probably be the particular deployment mode for the coming years in this band. And this basically closes the door for this combined use of the 3.5 gigahertz band with the 700 megahertz band. So we need to we will need to resort to other frequency bands, or this will be delayed, right, until new modes will be allowed. So basically, this is to illustrate that these kind of regulations, because why was this decision being made? Well, probably this is a very good. This 10 kilometers serves the urban regions well. So these kind of regulatory decisions, they are key to the rural, but they are not made with much, let's say, with much consideration to the rural. So I want to finish off. What is really needed to realize all this is we need to challenge this urban norm. We need to acknowledge these two distinct regimes and start building the networks from the outside in, starting in the rural and working our way back to the urban region. We need simple access to radio spectrum local initiatives. Regulators have a key role here. We probably need some form of national roaming. In many countries, that's simply not possible today, either by legislation or by convention among the national operators. And finally, we probably need to share infrastructure and share it with the emerging blue light services that in many countries are being operated today still separately. But most of all, we need to create awareness. People in the north of Sweden still think that the next generation will solve all their coverage problems. And while if we do not change our mode of operation, it will not. Thank you very much.